In this PowerPoint, we're going to lay down the groundwork for understanding these new kinds of equations and new kinds of functions. So uh, if it feels like it's going fast, a transition from polynomial functions to this stuff, it is fast, okay? But what we want to do is lay out the vocabulary and give you guys a preview of where we're heading. So if these objectives seem kind of overwhelming, don't worry about it. We don't have to read that list. Um, a rational function, which we're going to start working with, looks like this. R of x is equal to a fraction. And on top of the fraction, we have ax to the n power plus bx to the n minus 1 power plus cx to the n minus 2 power, and so on and so forth. So to sort of simplify this in your mind, think of this like we have a fraction, and in the numerator, we just have a polynomial expression. It could be a quadratic expression, it could be cubic, it could be quartic, that is fourth power, but it's just a polynomial like the ones that we just looked at before. Now, where this looks more complicated is because now we also, at the bottom of the fraction, have another polynomial expression, and it has its own coefficients, it has its own set of exponents, and so it has its own degree. Okay, so if the degree of the numerator is going to be this exponent n, then the degree of the denominator is going to be this exponent m. Okay, so why do they introduce it this way in most math textbooks? Well, it's because from a mathematician's point of view, this formula encapsulates every rational function that you might run into. But I think that for a college, an entry-level college student, this looks really complicated. So I think the easier way to think about this is that your fractions come in two parts. The top part's called the numerator, the bottom part's called the denominator. That's not new vocabulary for us. But the numerator, n, is going to be a polynomial. So you're going to have a bunch of terms on the top of the fraction. The denominator is going to have a bunch of terms on the bottom of the fraction. Okay? And so we need to break these rational expressions or rational functions up into the top part versus the bottom part. And we're going to start answering some questions by looking at, well, the bottom part tells us what about this function? The top part tells us what about this function, right? So we need to be able to break it up into pieces to answer some of the questions that you guys are going to see in the homework. Okay. So when we begin this, we're going to try to simplify it and start from like an easy problem and build up to a more complicated set of structures. So I don't want you to freak out too much, but what we're heading to are these graphs of rational functions that look like this. Okay. So over here on the right side of the graph, if you focus on just the blue lines, we have three parts of this graph, and they're separated by these gaps. And usually we don't have to put little dashed lines to indicate these gaps, but sometimes in ALEKS, they will ask you to find the vertical or horizontal asymptote. So once we start talking about these functions properly, probably on Wednesday, then we'll really get into what is an asymptote and what these gaps even mean. Okay. But for now, this is just where we're heading, right? The objectives are just a roadmap to take us there. We're going to start with our first step, which hopefully is going to be easier to digest. Okay. A rational expression. A rational expression is just an algebraic fraction, and it can be identified by the presence of a variable in the denominator. If you guys remember when we started talking about is this function a polynomial or not, there was one example in the previous PowerPoint where I gave you the function that had like 3 over x plus 2, and then I think I squared it. And then it had some other terms. And I said that this cannot be a polynomial because we have the variable in the denominator, right? So whenever you have a variable in the denominator, it's a rational expression and you're getting ready to work with a rational function, okay? So here's our first example. We have just 3 over x plus 2. Okay. And this probably feels like it's simple enough to work with. I'm going to write it down on paper so that we can kind of see some stuff. X plus 2. Okay. What you need to understand is that these rational expressions and fractions in general are just division problems. So we're going back over here. We have this rational expression. And a translation of this is that this is literally saying 3 divided by x plus 2. But like, this is even more complicated probably, like when you have parentheses and then a variable in there. So we're just going to keep writing them as a fraction, but we're going to be able to use these expressions and evaluate these expressions the same way we evaluate other expressions. So let's evaluate this expression when x is equal to, let's do something nice like x is equal to 4. So if I ask you, evaluate this expression 3 over x plus 2 when x is equal to 4, what do I need to do? Do you guys know what evaluate means here?
Plug it in.
Yeah. You see that word evaluate, you need to think plug it in, right? Take this x value, plug it in here. So I'm going to write 3 over 4 plus 2. And then if you need to, you can grab your calculator. Let the calculator evaluate it for you, right? We could do 3, get our nice fancy fraction. We could put 4 in parentheses just to be safe, plus 2, and I get 1 over 2. Are you guys okay with that?
Yes.
Just the mechanical process of plugging in our input value, which was 4, and I just arbitrarily, randomly gave you the 4 to plug in. And then our output value is 1/2. So like if you wanted to think about this like an ordered pair, then this output value is your y value. And so we would have the ordered pair 4 comma 1 over 2. So that's a point we could plot if we wanted to. Are you guys okay with that idea?
Yes.
So there's nothing scary or out of the ordinary about these. Do you guys want to give me another random x value so that we can evaluate this expression here?
5.
Yeah, let's go
Neg
with 5.
Negative number?
We can do a negative number. I'll split the difference. I think that Angel, was it, said 5?
Yes.
I'm gonna do -5 just so that I can sort of feed two birds with one feeder there. So to evaluate this expression, I'm gonna take my 3 over x plus 2. I'm just gonna put this as 3 over -5 plus 2. Okay. And then because this is a fraction and we don't want to be afraid of the fractions, the seasons don't fear the fractions. If you guys, that's a Blue Oyster Cult reference. If you listen to Don't Fear the Reaper, it's a classic. 3 over -5 plus 2, and I get -1. Okay. So for this problem, again, we just randomly chose -5. There's no rhyme or reason for that, but we have an x value. We have our y value. And so we could think about this as the ordered pair -5 comma -1 if we wanted to graph this. Any questions, comments about it? Does that feel kind of familiar? Like there's nothing new going on here, right?
It's not really like as difficult as long as you know like what X is, like the input.
Right. Right. And so like that's just graphing in general. Like you can choose whatever x values that you want to graph any kind of function, whether it's a polynomial function like the one we just looked at, or whether it's a rational expression or a rational function like the one we're currently working on. Okay. So all I'm doing is just trying to show you guys that to evaluate these expressions, we're doing the same thing. Okay, so you don't need to freak out just because it's a fraction. You just need to make sure you keep that calculator close if you're uncomfortable with fractions. Okay. But here's where we do need to be concerned. There are these certain input values called restricted values. And a restricted value is a value of x, or whatever the variable is, that forces you to divide by 0. Okay? And so maybe it's worth noting or recall you absolutely cannot divide by 0. That is a major violation in the world of mathematics. Okay? To verify that for yourself, you could say, okay, well, let me take a number and divide it by 0. So give me a random number.
42.
42 divided by 0. What does your calculator say? Well, it says error, divide by 0, right? I could try 3, like Audra recommended 3. Let's divide that by 0. I get the same error. You are not allowed to divide by 0. What about 0 divided by 42? Well, that's just 0. There's not an issue there. So you have to keep it straight in your head that if you have a number divided by 0, that says no. And so when we divide by 0, we're going to say that's undefined. Okay? But if you have 0 divided by a number, that says on, which means you can do that one. 0 divided by anything is going to stay 0. Okay? So those are two just like number facts that you kind of need to keep in your pocket. And we're going to really focus on this idea here. Okay? Because we're trying to investigate this expression 3 over x plus 2, right? The one that we were evaluating before. Okay. And so can you think of a value of x that if I plug it in here, it will zero out the entire denominator? What plus 2 would give me a 0?
-2?
-2.
Yeah, -2. So if I just sort of think about the denominator here, just for a little bit, you should know that x equals -2, if I plug that in, is going to end up giving me 3 over 3 plus. Sorry, I did the thing where I looked at the 3 and I just wrote the 3. My brain is not a smart brain, but it's the only brain I got. Okay. So I have -2 that I'm plugging in here, and it's plus 2 in the function. Are you guys okay with that?
Yes.
But because I chose x equals -2, and when I plugged it in here, I'm going to end up getting 3 over 0, which again is a violation of the laws of mathematics. So we're not going to get a y value. We're going to say that this is undefined. We can't do that operation. So we have an x value here, -2, but because we can't calculate the y value here, because we keep getting an error in our calculator, or we say that it's undefined, there is no y value for this x value. So we're going to say that x equals -2. Well, we want to avoid that. So we're going to write that as x slash through your equal sign. -2. And this is saying that x cannot be equal to -2 because it forces us to divide by 0, and we know that we're not supposed to do that. Okay, any questions, comments about that idea? You guys still writing this down? Okay. So what I want to do is really move on, because like this is the sort of the key idea for rational expressions and rational functions, that we need to be able to find these restricted values so that we can avoid them at all cost. Because essentially when we plug them into the expression, or if I plug it into the function, because it can't give you a y value, I like to think of it as it breaks the function. And we don't want to break the function. We want it to operate smoothly. We want to be able to give it x values and then get the y values back. Okay. So let's get back to the PowerPoint. So we want to really be concerned with the denominator of these rational functions, whatever they happen to be, right? We want to have a systematic way that we can apply every single time, a method of finding every restricted value, okay? And that process is basically just by setting the denominator equal to 0, okay? So if I just look at this rational expression, I don't care about the numerator here because the numerator can be anything, okay? I'm only concerned with the denominator because I can't divide by 0. I can't have a 0 in the bottom of my fraction. So to figure out what's going to cause the denominator to 0 out, I'm just going to take the x plus 2, or whatever the denominator is, I'm going to set it equal to 0 and then solve that equation. Once I solve that equation, I'll be able to figure out, well, oh, x actually cannot be equal to -2. And then we're going to say -2 is our restricted value, and I'm going to abbreviate that as RV so that I don't have to write restricted value out over and over again. Okay. So it doesn't matter what rational expression you get, to find the restricted values, you will always set the denominator equal to 0 and then solve that equation. Okay. And we'll do an example here in a little bit. Okay. So the next idea kind of stems from this idea of the restricted value. And so what I want to do is kind of switch back over to paper, because I think that this will make a lot more sense. So we've been just tinkering with this rational expression, 3 over x plus 2, right? And if we wanted to, we could write this as a function, f of x is equal to this business, right? What we did was we said this denominator, whatever it is, that cannot ever be 0. So to figure out what will make x plus 2 equal 0, we just set up that equation, solve it, x equals -2, but then we turn around and say, let's put a slash through our equal sign so that we know that this is our restricted value. Okay. Then you're going to run into some problems in ALEKS that are going to ask you to find the domain of your function. Okay. And this is going to be a natural like piggyback off of finding the restricted value. Okay. So usually when we define the domain, back in the day, we said it is the set of all the x values of the function f of x, right? That was one definition that we gave for the domain. The other definition when we were looking at graphs is we said it's how wide is the graph? And we go from left to right to sort of use interval notation to describe how wide the graph is. So if we put these ideas together, the domain of the function is the set of x values. And if we represent the x values as the x-axis, here's my x-axis, then my x-axis usually extends from negative infinity to positive infinity. Are you guys okay with that?
Yes.
Okay. Right now, I'm not concerning myself with range, so I don't really care about the y values, just the x-axis. Okay. But for this function, we said that we have a restricted value. And that restricted value is at -2. So I'm just going to put -2 in the middle of my number line. And if that number is restricted, I need to remove it from the domain. It cannot be there. So to remove it, I'm going to put an open circle here so that I take or cut the -2, that restricted value. I cut it out of the number line. Are you guys okay with that? Me removing that number? Okay. Now, I want you to use your imagination here a little bit and think about this number line or the x-axis like a piece of rope. And if I took scissors and I went to the number -2, which you guys know is restricted because we found that it was restricted earlier, it forces us to divide by 0, right? We want to get rid of it. If I cut this rope right here, how many pieces of rope do I have now?
2.
Yeah. If you have one piece of rope and you make one cut, you now have 2 segments, right? So I want you to think about it this way. You have now cut the number line. You've now cut the domain into 2 sections. And so we need to take account of what is the section over here on the left and what is the section over here on the right. Well, if we cut the number line into these 2 pieces, this side of the number line from left to right starts at -infinity, and then it goes all the way to our restricted value, but then it stops, right? Because that restricted value needs to be removed. So I'm going to put -2 here, and I'm going to put parentheses, because remember, parentheses means that the -2 is not included. Are you guys okay with that?
Yes.
Okay. The right-hand side, this other segment of the number line, it extends from -2 all the way to infinity. And I'm going to put parentheses over here on the -2 side as well, because we need to understand that that's not included, and parentheses means that -2 is not included. Are you guys okay with these 2 sections of the number line? Okay. So if you make one cut, if you have one restricted value, think about that as cutting your number line into 2 sections. And so now the domain has these 2 parts. So what we're going to say is that the function, and you don't have to write this whole thing, but I'm going to put 3 over x plus 2 has a domain d, and we're going to put -infinity, comma, -2. This is the left-hand side. And then what mathematicians like to do is put this U symbol wherever we made a cut.
Mm.
That's called a union symbol. And then we'll put -2 comma infinity to represent the right-hand segment of our domain. So because we had one restricted value here, we have two what are called sub-intervals of the domain. Or you could say two segments of the domain. So I really, as you're going through a problem like this, finding the domain, it really fundamentally relies on you being able to find the restricted values of a particular expression. Okay. So I want to go through another example. I'm going to make one up on the fly, but are you guys okay with this one here? Okay. So remember, this is being recorded, so if you need to go back and rewatch this section, please do that. Okay. So what I'm going to do is give you an example, ex, and I'm going to say we have the function g of x is equal to x plus 3 over 5x squared minus 10x. Okay. This is a rational function. And the first thing that we want to do is find the restricted values. And I say restricted values with an S because it really depends on the denominator. Okay. So like I said, we want to figure out the restricted values by taking the denominator only and setting that equal to 0. Okay. So I'm going to take 5x squared minus 10x, set that equal to 0, and then solve the equation to find the restricted values. Okay. Now, I think it's worth emphasizing this. You're only concerned about zeroing out the denominator, right? Because restricted values come from this idea that we cannot divide by 0. So we should never have a 0 in the denominator. I don't care about the numerator at all for this problem. And one mistake that students make every semester is that some people will just say, oh, I need to set the numerator equal to 0. No, we don't need to look at the numerator to answer these questions, right? You would be doing more work that's like pointless, right? So don't focus on the numerator here. For restricted values, you only care about the denominator. Okay. If you're okay with that, what kind of an equation is this? And I'll give a hint. It's a kind of equation that we know how to solve.
A quadratic equation.
It's a quadratic equation.
Equation.
So if this is a quadratic denominator, then we need to set that equal to 0, and we need to solve that quadratic equation. And usually we solve quadratic equations by factoring. So if I could factor this, then that's what I want to try. And both of these guys have a 5x in common. If I factor out the 5x, I'll have an x minus 2 equal to 0. So that's my factoring step. And then from here, I want to apply the 0 product property. So I'm going to set 5x equal to 0 and x minus 2 equal to 0. So if you need to skip some steps here, you can, but I just want to show all the steps. To solve this one, we're going to divide by 5. X is equal to 0. To solve this one, we add the 2 over to the other side. X is equal to positive 2. Are you guys okay with that?
Yes.
Okay. Now remember, we're not just solving these equations just to solve them. We were tasked with actually finding the restricted values. So these solutions were what we would get if we zeroed out the denominator. So these are our restricted values. So what I'm going to say is that x cannot be equal to 0 or 2. Okay, so if I needed to evaluate this expression or evaluate this function, you should avoid 0 and 2. Those are going to break the function. If you plug them into the equation, you're going to get undefined. Okay, you can do that on your own, but on the interest of time, we're just going to have to kind of sort of accept that. Okay, but definitely test it on your own to see if that makes sense to you. Okay. So we found our restricted values by setting the denominator equal to 0. We're back into the territory of solving some equations. So like if this is a quadratic denominator, I'm going to get my 2 restricted values. But if this happened to be like a degree 3 polynomial or a degree 4 polynomial, then you could expect to have 3 or 4 restricted values. Okay. So you should know how to solve polynomial functions and polynomial equations. That's not new material. I will tell you this though, for most of these problems you're going to see in ALEKS, you're either going to have 1 or 2 restricted values. I don't think that they give you 3 or 4 restricted values, and certainly we won't go any higher than that. So that's kind of the good news here. Okay, so we have our restricted values. If that makes sense, the next thing is we want to do is find the domain of the function, and we called it g of x here. And so to do that, I always recommend drawing the number line. So this is our x-axis, just like we did in the previous example. It goes from negative infinity to positive infinity. And then we want to say we're going to cut out our restricted values. So we have 0 here and 2 here. And since we're cutting those numbers out of the number line or out of the domain, if I have a rope and I make 2 cuts, how many segments of rope do I have now?
3.
I should have 3. So sure enough, if I make 2 cuts to my number line based on these restricted values, then my domain gets chopped up into 3 sections. The section here goes from negative infinity to 0. The section in the middle goes from 0 to 2. And then the section here from 2 to infinity is our last one, 2 to infinity. And so if I just put these union symbols in between my segments, that's the domain of this function. And so you're going to get some problems in ALEKS that say, find the restricted values, or find the values of x that could not be solutions for the equation, right? That means the same thing as finding the restricted values. And then if you run into those problems that say, find the domain of the function, then just realize that domain and restricted values essentially mean the same thing. They're kind of like 2 different representations of the same idea. So we need to find the restricted values and then sort of draw a picture of the number line, make those cuts so that we can figure out what the domain should look like. Okay, so one of these relies on the other. Okay. There is one more type of problem that you're going to run into that I want to like throw at you guys here so you have an example to go off of when you get into the homework. And so that's just the idea of simplifying a rational expression. Okay. So again, in the interest of time, I'm just going to move on. And we'll go through one of these examples. Simplify a rational expression. So first, do you guys recall that we can simplify a fraction like 12 over 48 by doing prime factorization? You guys remember when I did prime factor trees to simplify a fraction? I think I did it just like briefly when I introduced prime factor trees.
Yes.
Okay. So I'm going to prime factorize 12 and 48 here in my head. So I hope you guys don't feel too alarmed here. 12 is the same thing as 2 times 6. 6 breaks down into 2 times 3, and that's all the primes that I have there. 48 is the same thing as 2 times 24, and then we have 2 times 12. Actually, and then the 12 breaks down into 2 times 6. And then the 6 breaks down into 2 times 3. Okay, I think that's correct. All right, and I just wanted to sort of breeze through the prime factor trees because like when these are a fraction that just has plain numbers in the numerator and denominator, I sort of briefly introduced this idea that if we have common factors, we can cancel common factors to simplify or reduce the fraction. So if I have a 2 here, I can cancel it with a 2 in the denominator. If I have a 2 here, I can cancel out a 2 in the denominator. And if I have a 3 here, I can cancel out the 3 in the denominator. So what I'm going to end up with, if I cancel out everything on top, I'm going to have a 1 over, and I just have a 2 times 2 in the bottom, which is going to be 1/4. And that's fully simplified. So, you could check that in the calculator if you really wanted to. 12 over 48 is 1/4, and all should make sense with the world. Maybe you're confused on where this 1 comes from when I cancel out all the factors on the top, but it's really just this idea that a fraction's a division problem. And if I had 2 divided by 2 to cancel those out, I need a 1 as a placeholder, right? 2 divided by 2 is 1, 3 divided by 3 is 1. So we have like 1 times 1 times 1 on the numerator. Okay, maybe that's getting too far afield. The kinds of problems you're going to see in ALEKS will tell you to simplify something that looks like this. X squared plus 5x plus 6 over x squared plus 8x plus 12. Okay, so this is what we need to simplify. And they will say, simplify the rational expression. And it's very similar to this idea of simplifying a fraction. There's only 3 steps for this process. The first step is to factor the numerator. The second step is to factor the denominator. And then the last step, similar to what we did here when we crossed out common factors, is we're just going to cancel any common factors that we have. Sometimes I comically add a 4th step, which is for the love of God, stop. Okay? If you factor the top, factor the bottom, cancel common factors, you're done. Don't do anything else, because if you go one step further and try to make up some math, or you feel anxious and you do something, you're going to have taken the correct answer and then turned it into the wrong answer. And I'm sure that none of you guys want that. Okay? So think about this as a problem that has 2 parts. Let's focus on the numerator first, and let's factor it. So I'm going to put some scratch work over here. I have x squared plus 5x plus 6. And if I have a polynomial with 3 terms, how do I want to factor that?
AC.
I could use the AC method. Okay. Now, for those of you that are okay with the fast method,
Mm-hmm.
I know I need an x times x to get the x squared, and then I need the factors of 6 that are going to add to give me a positive 5, and that's going to be a 2 and a 3. And so I kind of skipped the AC method here just in the interest of time. Okay. This is my numerator. I'm just going to label as num. If you need to go through the whole AC method, please do so, but I just don't want to hold you guys back. longer than I have to. So that's step one, factor the numerator. Step two,
Well, so
factor the denominator.
denominator.
And again, because the coefficient here is a 1, we could skip to the fast method, which means I know I need an x times an x to get the x squared. I could ask myself, what are the factors of 12 that will add to give me 8? And
X
that's going to
plus
be
2, x
2
plus 6.
and 6. So it's x plus 2 and x plus 6. And this is going to be my denominator. I'm going to label that as denom. Okay. Again, if you need to go through the AC method, go through that process, the full process. But once we factored the numerator and factored the denominator, we're going to rewrite our expression as x plus 2 on top times x plus 3. That's our numerator. Our denominator in factored form is x plus 2 times x plus 6. And then our third and final step is to cancel the common factors. Which of these factors is going to get canceled?
X plus 2.
The x plus 2's get canceled because they're the same. So what I'm left with is x plus 3 on top and x plus 6 on the bottom. And then we're done. If you want, your fourth step is for the love of God, stop. Okay? This is your final simplified answer. Okay? So that's all you have to do. Don't make it more complicated than you have to. I've been saying since we started Module 2 that factoring was going to be so important for the rest of the semester. Well, here it is, right? We're going to have to factor to solve equations. We're going to have to factor to simplify rational expressions. So if you're having trouble with that, make sure you're getting the help in Math World and like really refreshing on those factoring methods if they're really giving you trouble. Okay? Sorry for going over. That's all the time we have here. So I'm going to end it there. We're going to pick back up tomorrow and finish out this PowerPoint and really get into solving rational equations. Okay.